Right, well, thanks to Nimbus here for the opportunity of sharing some of the information that we've been working in our group in Kansas State with some collaboration with the folks in Australia. So this is basically the title of the talk that I'm having for you guys today. Let's see. Anyways. It's not moving.
Oh, on the remote control, if you there's a wheel on the side.
Yeah.
Pull that towards you.
Okay.
Yeah.
Okay, got it. Well, basically today the story I'm going to tell is about wheat, but most importantly is what's happening with the wheat after we harvest it. So we have the grain, but the grain should be stored, right? I want to emphasize that this is a very dynamic process. It's a very complex network, and basically we have to think in terms of where the wheat is going. Finally, could basically reach the milling industry, or some exportation ports just to go overseas and to be sold. Everything starts in the field during the harvest time. Here is around July, the 4th of July, depending on the state that you're working on. And after that, the grain is going to be stored in different structures. One of the smallest one are the grain bins, and this is a very nice picture of these structures in Kansas. But we have different sizes, different structures too, like this country elevator. Some of them are really big, they are massive structures. And I want you, please to pay attention to the proportion here of the tracks compared to the building. So we're talking about millions of pounds sometimes of wheat just stored in this structure. But not only that, we have also the terminal elevators where the volume is just gigantic. Anyway, when I'm talking about this, basically we have some problems. They could be pathogens, mycotoxins, but most importantly for this talk today are going to be insect pests. And these guys, they are moving through the whole system. We can have some grain that is harvested here, can be contaminated with some of the insects, and it's going to start some movement to the different structures where we are storing the wheat. The question that I really want to ask is, what is the link between the components of this network? And it seems very obvious and simple, and it's human transport. We can see that basically when we have our grain in the farm storage, we take our grain, we put it in a truck, and we ship it to the different places. Or if you're using train, for example, the railroad also is a very nice way to transport this system. In the United States, let me just say this, the barges in the Mississippi River are also very important for the transportation of the wheat. With this, I want to say that I like to use the network structure of this system, basically, potentially to use it to improve the management, to improve especially the management for pest resistance. But also, we want to illustrate the potential for a store-grade system as a model system for grade science, ecology, and network analysis, and any other branches of science that are basically involved with this. You guys may know this already. We produce around 10–11% of the total amount of wheat worldwide, and the United States ranks between the second and the third place. So this is a really big deal here in the United States. But most important is where this wheat is being produced. And as you can see here, basically the Midwest is having the largest concentration of spots of wheat in terms of production and also shipment and movement. Also, we find some spots here in the Pacific Northwest, here and near North Dakota. And when we look at the data, this is what we found. We, in fact, found states like Kansas, North Dakota, that are basically ranking in the top of terms of wheat production. Let me just change gears quickly for the folks that are not really familiar with network models. I want just to say that a network model basically is made up to two things. The first one is the node or the vertex, and the connection between two nodes are going to be the links, and that is showing us the level of interaction between the pair of nodes. What a node could be pretty much everything. So we can talk in terms of spatial location. We can talk about countries, regions, counties, fields, plants, levels, but also we can think in terms of entities like species, genes. We can even go to the level of molecules. And the links of the edges of these, they could be, for example, the strength or likelihood of influence of different nodes. Triggering, for example, for genes, the information flow, and of course it's going to be depending on the environmental variables. Having this knowledge in our mind, I just want to say that I'm going to be working basically with the major states involved in production and transportation of wheat. We end up working with 37 states, and also the links in our, that are connecting our nodes are showing directionality. So basically, I start with this map showing 37 states involved with wheat production, and after running the model using the iGraph package in R, this is what we found. Every single node is showing us here the states that are involved, and we can find 3 different types of nodes. The first one, some states are basically sending wheat. They send it, like in this case, Wyoming goes, for example, to Utah or Idaho. A second type of node, like Virginia here. Virginia is one of the receivers of wheat, for example, and it's coming basically from Ohio and Illinois. But we have also a third type where some nodes are basically receiving and sending, which also is going to change the structure of the network. What are the applications on this? Basically, let's say that we have an outbreak of a pest resistance, for example, and it happens here in South Dakota. So I really want to know, using the network model, how fast or what would be the shortest path for this pest to go, for example, from South Dakota to one of the exportation ports, and let's say South Carolina. Thinking geographically seems like really far away, and probably can take some time, but running the model, we can see that the shortest path is going to take only just 2 steps, and it's going to be going through Illinois. Sorry. In this table, I want to summarize. Basically, we run the analysis of the shortest path for every single state that is involved in our network. And here in this table, I'm showing, for example, some states that are really very important in terms of sending wheat, like South Dakota. Some of them are exclusively just receiving the wheat, and we have, like a big amount of states just in the middle. Another case that we can basically make with this model is we can weight the volume of wheat that is transported, and here the links are showing us that what are the states, what are the nodes that are basically sending the larger amount of wheat, and that's represented basically, as I said before, for the weight. And I'm keeping the size of the states constant, of the nodes constant. But how about the production? Let's say that I want to see, in terms of the network, what states are basically showing the largest production. And as I said before, Kansas, North Dakota, those the size of the node is telling us how important, how big is the production of the wheat in these states. The coolest thing is that we can put these 2 things together. So here we can show, for example, we can see the movement of the wheat and also the production in terms of the nodes. So this is basically a graph summarizing these 2 results, and we can infer different things. What happens if we have an outbreak in one state? What would be the shortest path? How can we connect, for example, the different nodes, exportation ports versus industry, production, and etc. And also using this analysis, we can have other measures. In terms of the network, we can, for example, identify the average path length, meaning that if we want to go, in terms of the average, from one node to another, it's going to take around 2.1 links. Also the transitivity, which is another measure, excuse me, if the transitivity is close to 1 or 1, very nice, very excellent flow in terms of the transitivity. If it's 0, there is no connectivity, there is no flow. We are around 0.5, which is a good number. And also in terms of the path length histogram, here we take, well, I'm sorry about this, but we take here the shortest path, and basically we are estimating what states are having just one shortest path, what kind of nodes. And the number here, if I don't recall wrongly, this is around 130, 35 probably. So that means that 135 shortest paths are having just one link. This is around 180, meaning 180 nodes are having a shortest path of 2 links, and so on. Talking about between the centrality, basically this information is telling us how many shortest paths are going through one state. And here, Kansas, we can identify as one of the most important, because most of the shortest paths are going to that state. So what happens if we have, for example, an outbreak of pest here? What happens if the resistance basically is showing up there? So it's going to be very important in terms of the network and where the problem is going, for example. Another measurement, a maximum flow. Let's say that I want to see what is the maximum flow that we can be transported from one state to another one. And let's keep in mind that with the wheat, our pests are going. So we are transporting our wheat, but the pests, the problems, are going also with our grain. Some of the risk factors of pesticide resistance that we have detected, basically the number and the quality of the fumigations, the kind of fumigant that is being used, for example, the effectiveness, is the structure completely sealed or not? Are these sublethal doses, as you said before, are basically causing the resistance, which is, there is some evidence for the Australian folks showing that happening. Is the number of insects high or low? How that is going to affect our model? The weather conduciveness, the temperature is okay for the development of the resistant pest or not, humidity. And again, which is very important here, is the movement of the equipment, not only the combines that are going from the south to the north here during harvest time, but also let's think in terms of the trucks. There is always some grain in the trucks, there is always some grain in the wagons in the train, and those could be basically seen as an issue for the pest, and resistance can just start generating there. Some of the challenges and the problem that we have, well, the most important, I would say, is uncertainty. There are some also legal issues and some practical issues. Some people, they spray, they fumigate every 2 months. That's it. But of course, we know that the larger the exposition to the fumigant, we can basically just increase the pressure for the development of resistance. Some tolerance levels in some countries like Australia is 0, no insects in our grain for exportation. We allowed some numbers. The sampling methods, they are not completely efficient in terms of determining how many pests we have in our grain. And let me just say that we are working basically in terms of the resistance to phosphine, and these 2 insects are basically our guys. We are very interested in the development of the resistance to phosphine, because it's basically the last strategy that we have to control these 2 insects in Australia and United States. I've been talking mostly about United States, but also the idea is to work with the Australian guys, with Australian people. And here I'm just showing the network, the rail network in the eastern part of Australia. And our ultimate goal is basically to answer questions like this. What distribution of pesticide use can store grain networks tolerate before pesticide resistance spreads through the network, for example? If pesticide resistance is detected, what locations are likely involved, and how can mitigation be optimized? So we are thinking in terms of mitigation, we're thinking in terms of management, and how can we avoid, for example, the appearance of resistance. And with this, let me just basically acknowledge the CRC in Australia, which is one of the big funders, and also Kansas State University, and Karen Garrett and Sarah Thomas, who are also part of our group. And of course, I have to say thank you to the folks in Australia and Nimbus for the chance to be here and telling this story. So with this, I'd like to take any questions that you guys have. Thank you.